Okay, for this number, this first one, they say let f and g be functions given by f of x equals e to the x and g of x equals ln x. Okay, find the area of the region enclosed by the graphs of f and g between x equals a half and x equals 1. Okay, so this is a calculator one, so we'll kind of basically do all this in the calculator. So first let's put them, if we look at the calculator, put them into y1 and y2. Okay, so now, yeah, let's change the window. Definitely, they say half to 1, so we'll go from 0 to 2 maybe. And, we don't know how high they go, how high it goes. Let's graph and see. Okay. So maybe we want to increase the y value to get both in view. Yeah, okay. Okay, so now they're both in view. So now we can see that the blue one is the e to the x, and that's on top, and then the red one's the ln x on bottom. So now we know when we integrate, we'll do integral. We'll do it by hand first. So now we know we're going to do integral from 0 to a half. Whenever they tell you between two x values, those are going to be the limits. And then we'll do the top function minus the bottom function. Okay, and then for us in the calculator, we'll go from 0 to a half. And e to the x was y1. And then ln x is y2, so it should look like that. Okay, so let's go back to the calculator. Okay, yeah, just making sure that that was right. So e to the x was y1. Yeah, so now we'll do math 9 to get the integral. And then just, whoops. Oh, it was a half to 1. Oh, I messed that up on my, yeah. Not 0 to a half. Okay, and that should be it. Okay, so here I messed up. I don't know why I did 0 to a half. So this should be a half to 1. Let me correct it here. Okay. And then that was, what was that in the calculator? Let me see. Oops. I think that was 1.222, something like that. Okay. Okay, 1 second. Okay, actually it's 1.223. That's what that is. Okay. So next one. No calculator one for this one. So they say the expression, the integral from 0 to 9 of 12 minus 4 root x dx gives the area of a region R in the first quadrant. Okay, write an equivalent expression using horizontal rectangles. Okay, so they just mean right now, you can see this is a dx, and this functions in terms of x, and so this 12 must be a function in terms of x always. This would be y equals 12, y equals 4 root x. But these are in terms of x, y equals something in terms of x. The limits are x values, and that's using vertical rectangles. Okay, if we use horizontal rectangles, everything changes to y. So this will change to a dy. These two functions will have to change to, well, actually let's graph it first and see what happens. Okay, so if we first just graph these two functions, do this off to the side. Okay, so we'll go from 0 to 9. All right, and then y equals 12. Just that. y equals 4 root x. So you can see if you plug in 9 into this, into 4 root x, if you look at y equals 4 root x, if you plug in 9, so 4 root 9, that's 4 times 3, that's 12. So then that'll be a point. And then we know if you plug in 0, you get 0. Just if we're doing it by hand. Okay, the function will look something like this. Endpoint there. Okay, so the area that we're looking for is just all of this area here. Okay, and that's what this integral is, right? Finding all the area from 0 to 9 in between y equals 12 and y equals 4 root x. That's what that is. But now they want us to do it the other way. So we're going to do everything in terms of y, which means we, if we look at this area here, we want to do what function bounds this area to the right, which is 4 root x, and the function that bounds it to the left is x equals 0. So now if we're going to change everything to x equals, so we'll look at x equals 0. And then if we go down here, if it was y equals 4 root x, okay, so if we square both sides, and then we can divide by 16, and we get x equals y squared over 16. Okay. So now, and then we can see this area, we have to look at the y values that it goes to and from. So as far as in terms of y, everything's in terms of y now. The lowest y value that bounds this area is 0, and the highest y value is 12. So you can see that 12 now became part of the limit. So here, let's do that. So now we know we're going to do from 0 to 12. And then our right function is y squared over 16 minus, and then our left function is technically 0. We don't have to write that obviously, but just to show work. All right, that's it. And then they say just write an equivalent expression using horizontal rectangles. So that would be it right there. So that would be like our final answer there, and just like that's the final answer up there. Okay, so another no calculator one for number 3. They say let R be the region in the first quadrant enclosed by the graphs of f of x equals 8x cubed and g of x equals sine pi x. Find the area of region R. Okay, so we, anytime you're finding an area of a region, the function's already given in terms of x, y in terms of x. So let's see if we can do top minus bottom. That'll be easier. Then we don't have to change those functions. So if you look at this area here, this is the sine graph on top, and then this will be that cubic graph on bottom of this area. And we can see the sine graph is on top the whole time, and the cubic graph is below the whole time. So that's perfect. So we'll just do everything in terms of x. So okay, so to set it up, we can see the area goes from, this is all going to be in terms of x. So the area goes from 0 to 1/2. So those will be our limits. Okay, and then we'll do the top function, which in this case is sine pi x, and then minus the bottom function, 8x cubed. All right, and so now we just have to, so this is the area, whatever we get for this, and so now we just have to evaluate this. Okay, so first step is going to find antiderivative. So the antiderivative of sine is negative cosine. We could do u substitution, but I'm going to kind of do this quickly. So it's going to be negative. So technically it's negative cosine pi x, like that. But think about it, if you take the derivative of this, negative cosine pi x, you get sine pi x times pi. So if we don't want a pi, times it by 1 over pi to cancel out that pi. Okay, and then you can even just check to make sure that this, if you take derivative, gets you back this, which it should. Okay, then the next one, this is 8, and then taking the antiderivative of x cubed, just a power rule, so add 1 to the exponent and divide by the new exponent. Okay, and this just cancels out to be 2x to the 4th. Okay, and then we evaluate this from half to 0. Okay, so let's plug in a half. So it'll be negative 1 over pi. And this will end up being cosine. If you plug in a half to x, that's cosine pi over 2. Okay, and then if you plug in a half to the 4th power is 1 over 16. And then times 2 will be 1 over 8. Okay, and if we plug in 0, we get, here that'll be a cosine 0, so it'll be still negative 1 over pi, cosine 0, and then just minus 0, so we don't need that. Okay, cosine pi over 2 is 0, so that just goes away to 0, so we don't have to evaluate that. And so we'll just end up with negative 1 over 8. Okay, and then this is minus a negative, so that'll be plus. And then cosine 0 is 1, and so that's it. Okay, and then we can just leave our answer like that. Okay, so for number 4. Get this situated. Okay. And this was an FRQ on one of the actual AP tests. I forget when, 2017 or something. Okay, so they say let R be the region in the first quadrant enclosed by the graphs of f of x equals ln x and g of x equals 5 minus x. Okay, they say the horizontal line y equals k, some horizontal line, divides this region into 2 equal areas, right? But do not solve an equation involving integrals whose solution gives the value of k. Okay, so what they're saying is there's some horizontal line, I'll estimate it about right here. Maybe something like that, probably a little lower than that. So they're saying this is some horizontal line, yeah, it should be smaller than that. Here, let me actually fix that. Not smaller, but lower. Doesn't really matter, but just to get an idea. Okay, so this is like some horizontal line, y equals k. So there's some horizontal line so that this area down here equals this area up here. Okay, other ways you can do it. You can say, another way to say that is, you can say, like, for example, this area is twice the whole area, or half the whole area, or this area is half the whole area. Or you can say this area equals this area. Okay, so those are kind of 3 options of equations, just based on things that are true, areas being equal. Okay, so now we really have to do right minus left. We can't do top minus bottom, or at least not as easy, because we can see, like, if you do top minus bottom, like we want an expression that gives this area here, and we want an expression that gives this area here, and then we can set them equal to each other. But, like, let's say if we wanted to find an equation representing this area, we could do it. We would just do, like, we could find the x value of this intersection, and then we could do an integral from and then find the x value of the intersection for this. And then we could do the integral from here to here of this top function minus this bottom function. Okay, and then we could do the same thing for this area here, this top minus this bottom, and then just go from this x value to this x value. But that would be kind of two different integrals, and I don't know. But notice if we do right minus left, for example, on this top part, this is to the right the whole time, and this is to the left the whole time. Okay, so that's one thing. So that, and then same thing here. This is to the right the whole time, and this is to the left the whole time. And it'll be nice to do that because then we can just integrate. Integrating each of those integrals will be the same because it'll be this minus this for one and this minus this for the other. So it'll be the same functions inside of our integrals that we're subtracting, but just the limits will change. So that'll make it easier to evaluate. Here we don't have to evaluate, but if we had to. Okay, so if we're going to do right minus left, we have to get everything in terms of y. So let's do that now. Okay, so they say f of x equals ln x, so we'll change that to y equals ln x. And then if we're going to solve this for x, get x equals, really raise each of these to the e power. And then e to the ln of something cancels out, and this just equals x over here. So this is really x equals e to the y. Okay, so that's our that's our left function here. Okay, so let's do the same thing for the other function. We'll first call it y equals 5 minus x. And then if you solve this for x, people can do that on their own. 5 minus y, just kind of add x to both sides and subtract y from both sides. Okay, so that'll be this function here. Okay, so now if we're going to do find out this area here, we have to, since everything's going to be in terms of y here, I'll set up the integral for the top. So let's say this is going to be the top right now. Okay, so this will be some integral. Figure out the limits. We know the right one is 5 minus y. And then the left one is e to the y. Okay, so the limits are going to be, and so I'll say this is the top. Limits are going to be whatever this y value is to whatever this y value, the y value of this point is. So just kind of looking at the general area, what's the smallest y value that bounds this area, and what's the biggest y value that bounds this area? Okay, and that we'll have to find in the calculator. Actually, we know this y value, is k. So really, we just have to find this y value up here. Okay, so we'll do that in the calculator in a second. Okay, so let's set up the other side though. So now this bottom area, still the same right minus left, same functions. Do some integral. And it's the same thing. So it'd be 5 minus y, that's on the right. And e to the y is on the left. dy, covering the calculator. Okay, so that's the expression. And then we know, like for example, the top one. Actually, here, let me write this. This is the bottom. Okay, so for the top half here, we know it's going to go from k to something. So we know k is going to be the bottom limit here. And then for the bottom one, we know this is going from 0 to k. Okay, so the only thing we really have to get is this top limit here according to the y value of this intersection here. Okay, so let's do that in the calculator down here. Okay, so definitely go to y equals first so we can type in these functions, and we're going to type in the original functions. This is the y value. There's a way to do it, typing in these functions that are in terms of y, but just better to, as long as these graphs are given, we'll just graph these original functions that are in terms of x. Okay, and we can see what the graph is, so we can see our window, 0 to 6, and then 0 to 2. We'll put it, okay. So we want the y value of this intersection right here. So calculate intersection. Get the cursor as close as you can to the intersection, and then just hit enter 3 times. 2, 3. Okay, so that's our y value there. Okay, so just little things. We'll do second quit, and I'll do store, but clear that and get answer store to set it to A. But that's the x value. So we have to plug that back into one of the functions. It doesn't matter which one. So we can plug it back into, I'll plug it into y1. I don't know why I grabbed that like that, but we could have typed A also. If I record this earlier. Yeah, just so we can see. So, and if you plug this into y2, and here I'll do A this time. Just since I did it, yeah. So you get the same value for whether you plug it into the first or second function. Okay, and then that was it. Oops. And then that got us so that's our y value, 1.307. Okay, and they say write but do not evaluate an integral expression involving integrals, whose solution gives the value. Okay, yeah, so if you solve this, and these aren't plus. I don't know why I did that. It's not plus. These are equal. This is the top area, and this is the bottom area, and we want these two areas to be equal. So I messed that up. Okay, and that makes sense. This is the equation that if you solve this equation, this would give you that value of k. That makes those two areas equal. Okay, so this is another no calculator question. They say let R be the region bounded by the y-axis. Okay, in this problem, the y-axis here. The vertical line x equals 2. The horizontal line y equals 6. And the graph of 4 ln 3 minus x. That must be that one. As shown in the figure below. Okay, write but do not solve an integral expression that gives the area of region R using vertical rectangles. Okay, this will be easy using vertical because first off, if we're going to be using vertical rectangles, that just means doing top minus bottom. And here for this area of the shaded region, it has a clear top the whole time and a clear bottom the whole time. And our functions are already solved in terms of x, so, and we know the limits, 0 to 2. So this one will be easy to do. So we'll do integral 0 to 2. And then we'll do the top function is y equals 6 minus the bottom function is that weird one, 4 ln 3 minus x dx. Okay, that's it. Okay, so obviously that would be the easier way, or obvious once we do it the other way. So we'll compare. Part B, we're just doing it for practice, so you wouldn't actually do this, but let's do this for practice. Okay, so we're going to solve this just like one of the other ones that we did, where they asked us to give the area using horizontal rectangles. So we'll So that means we're going to do right minus left, and everything will be in x equals. Okay, so this is the x equals 2. Oh, actually little things here. Let me mark up on this figure. So you notice, if you do right minus left, in this region, this is the right and this is the left. But if you go below here, then this is still the right. This is the right the whole time. But now this becomes the left here. Okay, so notice we have to figure, we're really going to have to do like this area here first. Oops. This area of this kind of rectangle here. And then we'll do this area next. So we have to do 2 separate integrals. Okay, let's do the bottom one first. Okay, so we're going to do right minus left. Okay, so the right function here is x equals 2. And then this left function, we'll have to solve for it. So we know the function starts out y equals 4 ln 3 minus x. We'll have to solve this for x. Okay, so we have to divide by 4. And that'll cancel out that 4. And then we'll raise both sides to the e power like we did before. And then that cancels out the e and the ln. Okay, and I'm going to kind of switch them also. So we'll write 3 minus x equals e to the y over 4. Okay, and then if we solve for x, we'll have to subtract 3 from both sides and then negate both sides. Subtract 3 to get rid of that 3, and then negate both sides to get rid of that negative. I'm just going to do that all at once. That'll be 3 minus e to the y over 4. Okay, and that's this one here. X equals minus e to the y over 4. Okay, so this area we know the right function now is 2, and the left function here is 3 minus e to the y over 4. So the only thing left is to get the limits. So everything's in terms of y, so the smallest y value that bounds this region is 0. And now we need this y value here, and we're going to need that for the other integral anyways. So we really have to get according to where this intersects this line. So we really want to know, like if we look at the original function, y equals 4 ln 3 minus x. If x is 0, if this x is 0, that's the y value. So you can see, like, if you plug in 0 for x right here, you just get 4 ln 3. Y equals 4 ln 3. And that's like this y value here. Okay, so now we can do everything. Okay, and then let's set up the second integral also. So this is still x equals 2 for the right. And then this left here is x equals 0, just the y-axis. Okay, so the first integral, I'll do the bottom one. Okay, so that'll go from 0 to 4 ln 3. Okay, and then the right function is 2 minus, and then the bottom function is 3 minus e to the y over 4. Okay. Okay, so that's the bottom area. Oh, whoops. And then dy. Actually, I'll do it down here. And then plus. Okay, so that was the bottom area. So now we'll do the top area. So that goes from kind of, so this top area up here, the farthest down it goes is 4 ln 3, so that'll be our bottom limit. And then it goes up to 6. 6 is the highest y value here. Okay, and then the right and left functions here. The right function is 2, and the left function is 0. And we don't need that 0 really, but I'll do it just to show work, and so that's it. Okay. Really, all of this is our answer. Okay, next one. So, multiple choice question, no calculator. They say, which of the following integrals correctly gives the area of the region above the x-axis but below the curve of that? Okay, so let's draw a picture. Okay, so this is, the x squared is negative, so this is a parabola facing down. And then let's actually, if it's a parabola facing down here, and we want the area that's bounded between the function and the x-axis, we really want to find out what are these x-intercepts, because the top half is going to hit those x-intercepts, and then that'll be the bounds of our area, which will end up being the limits of our integral. So we really just want to find these x-intercepts. So really, let's set this equal to 0 and solve for x to find the x-intercepts. Let's do that now. Okay, so here I'll write this, 14. Okay, but we want the x to be, the x squared to be, we want to rearrange these so the x squared comes first, and then the x, and then the 14, and then we also want the x squared to be positive. So I'm going to negate everything and switch the order at the same time. This would be a positive x squared. This would be a positive 5x, and it'll become a negative 14. Okay, then we factor. Okay, so now we know, like, if we were going to graph this, this would go from negative 7 to 2. And we don't have to be perfect. It would look something like this. Okay, and then this is the area that they're looking for. Okay, that's the area that they say, just to see correctly, gives the area of the region above the x-axis, but below this curve. That's this area here. Okay, so now we know the limits, and now this is on top the whole time, this function, and so it's just really the integral of this function. So, and we can see, so negative 7 to 2 of the function, and that's just d. Okay, so number 7, part A, and we can use a calculator, although we don't really need a calculator, but they say write, but do not solve an integral that will compute the area of the region bounded by x squared plus y squared equals 4, between x equals negative t and x equals t, whenever t is between negative 2 and 2, or equal to negative 2 and 2. Okay, so let's first draw this graph. X squared plus y squared equals 4. So that's, this is something just have to memorize. This is the graph of a circle, and then the radius is 2. This will go from negative 2 to 2, and above to 2, below to negative 2. All right, so they want the area of this, but they want it between negative t and t. So they want it, like, let's say, maybe this is the line negative t, and then that means, to make it symmetric, maybe that would be t there. so they want, like in this case, they're wanting like this area here, just in between those two t values, negative t and t. Okay, so if we're gonna do right minus left, or top minus bottom, sorry, so we want to do like, this would be the top, you know, whatever this function is on top, and then this would be the function on the bottom. And so all we have to do is figure out what this function is and what this function is, and then subtract them. And then we'll just, our integral will go from negative t to t. Okay, so let's do that first. Not much room, so this will be integral from negative t to t. All right, and then if we're going to do top minus bottom, we have to solve this for, you know, y equals something in terms of x. And so let's do that. I'll do that kind of down here. So if you have okay, so you could solve for y squared first, subtract the x squared, and then when you square root both sides, you get y equals plus minus. So you're like here, you're like square rooting both sides, and then you get y equals plus minus square root of 4 minus x squared. Okay, and we can see like this top half here is y equals square root of 4 minus x squared. That's the positive one. And then the below is y equals negative square root of 4 minus x squared. Okay, so the top half is the positive square root, and then the bottom is the negative square root. Okay, so if we set up our integral, be the top function, and then minus the bottom function, minus a negative, and then that's it. Okay, so technically plus, you know, for those two. Okay, and it says write but do not solve, so that's it. So that's an integral expression. Oops. An integral expression that would give that area. Okay, and then part B, they say to actually evaluate the integral for t equals 2. So if t is 2, this goes from negative 2 to 2. They want just the area from negative 2 to 2. And that's just really all this area. And so even if we could set up the integral, but we're not going to actually integrate it to get an answer. So we can kind of do this a couple ways. And tell me if this makes sense. You could do the integral from negative 2 to 2 of this top function, and that'll give you this top area, and then just times it by 2, and that'll give you the whole area, since this area equals this area. So hopefully that makes sense. We'll do 2 times the integral from negative 2 to 2 of that square root function. Okay, and then since this is a circle with a radius 2, we'll just do pi r squared. We know that we're just asking for the area inside that circle. And since the radius is 2 and we do pi r squared, that's just 4 pi. And that's it. Okay, and then the last problem is a calculator problem. Okay, so they said let R be the region bounded by y equals sine pi x and y equals x cubed minus 4x as shown on the right. Okay, find the area of region R. Okay, so this is nice. Our functions are already in terms of x. For this, there's a clear top and a clear bottom. So if we do, we can see the top is sine, this little sine wave, and then the bottom, this must be the cubic function. And then if we do top minus bottom in our integral, if we do sine minus the x cubed minus 4x, we can integrate each of these functions. Okay, so that'll be the perfect thing to do. Here, I'm going to blow this up. Okay, so this is a calculator? Okay, so that's good. So we'll set up the integral by hand and then just type it in the calculator. Okay, so setting up the integral by hand, we can see this area farthest left and right is 0 to 2. Right, everything's in terms of x. The farthest left this goes to 0, and farthest right this goes is to 2 in terms of x. Okay, and then we'll do the top function minus the bottom function. And we got to be careful with parentheses. Okay, and that's it. So let's go to the calculator. Okay, go to y equals. Kind of always when we were given multiple functions, we'll just type those functions in first. Oh, whoops. I think I forgot. I recorded these calculators questions, the calculator part earlier, so I think I just didn't do it. But this you just type into the calculator, and it ends up being 4 as the answer. Okay, so I'm gonna skip just all that is doing math 9, and then just typing this in just like it's written. Okay, so let's go to the second one, and then that's what we're really, or part B is really what the calculator will have to use it for. Okay, or another thing that's we'll talk about. Okay, so part B says the horizontal line y equals -2 splits region R into 2 regions. Okay, write but do not solve an integral expression that would give the area of the part of R that is below this horizontal line. Okay, so they're saying if you did some horizontal line y equals -2, right here. Okay, they say write but do not solve an integral expression that would give the area of the part of R that's below this line. So the part of R that's below this line is just all that area there. Okay, so we have a clear top function, y equals -2, and a clear bottom function, y equals x cubed minus 4x. We could integrate each of them by hand, but we're using a calculator, so it doesn't matter. And so the only thing we need is these x values here, where the functions intersect, because those will be our limits. So let's set up everything first, and then we'll find our limits. So we know we're going to do some integral. We'll figure out the limits in a second. The top function's -2, and then the bottom function is that cubic function. Okay, so let's find the intersection, and that's what the calculator is for. So we'll type in these two functions. -2 is one function, and then the cubic function is the other. So we'll go back to the calculator. Okay, so we'll definitely change our window according to the graph. X min and X max, 0 to 2 for sure. Y min maybe -3 to 0, min and max. And that'll show up those intersections, just as long as those intersections show up. So now do second trace, which is calc. Go to number 5. And then we'll just do this twice, get the cursor close to the one intersection, hit enter 3 times. Okay, and then we'll go back to a blank screen, second quit, hit store, clear since we didn't get answer, store, and we'll store that x value as A. Okay, do the same thing, second trace calc, calculate the intersection, number 5, go to the other one, hit enter 3 times once we get close to the other one, and then we'll store that other x value as B. Okay, second quit, store, we get answer so we don't have to clear, second B, alpha B. Okay, and so now we can set up so those are our limits. Let's go back to the problem. So now our limits, our lower limit is 0.539. And our top limit is 1.675. 1.3 should be good. Okay, you want to only round the final answer to the thousandths. The other intermediate values you should not round at all if you can help it. Okay, and that's the nice thing. So so I'm going to go on and integrate this, but we don't really need to. So now we can integrate it if we wanted to, if they asked us to, which they don't, but then we could just do alpha A for the bottom limit, alpha B, so those will be exact values. And then we can do y1 minus y2. Okay, this is just for practice. They don't ask us to actually get the answer, but just to see how easy it would be, because they'll ask us sometimes. Okay, so that would be the answer if they ask for it. But okay, but here this is all they wanted, an area, an integral expression that would give the area of that region that they described. Okay, and that's it.